My computer's really slow at processing video. So while I was waiting for our lecture video from Tuesday to upload to YouTube, I'm like, ooh, I'll do an art project. And I grabbed some scissors. So, everybody up? I know it's early. Come grab a couple of these, different shapes, different colors. We're going to make boxes. And talk about functions and function notation in reality.
One of each?
There's probably not enough to get one of each, but grab a couple different ones. I didn't have that much scrap paper. And on one side or the other, each of them has a little number written by the cutout. That's all the pieces I have.
That's okay.
Yeah. You can sit with someone else and, yeah, oh, there's, all right. So, you perhaps have seen this question before, but there's a variety of the problem setup. You have a piece of paper, cut out square corners, possibly a discussion of why do they have to be square, and then fold up the edges to make a box. So, each of you has an 8.5 by 11 sheet of paper that has 4 corners of the same size cut out, at least close as I can with scissors. And by one of those corners, you'll see what size it is, but these are in inches. There's either a 0.5, if you have one with a little itty bitty corner cut out, a 1, 2, 3, or a 3.5 written there, because I couldn't cut any larger than that without just messing up the paper. But the idea is, if you cut out these corners, you can fold up the flaps and create a box of varying sizes depending on how large those corners are that are cut out. So, just thinking in general, think about your particular box. Write down on a piece of paper what computation you'd need to do in order to find the volume of your box. Remember, volume of a box, 1 times width times height. And the paper started out as 8.5 by 11, because that's what size our printer paper is for the most part. So see if you can write an expression for your particular box that expresses, or boxes, that expresses the volume. We're going to talk about all of these. And some patterns and some notation. This isn't geometry class. Our goal isn't how do you find the volume of a box. It's how are all these pieces related and how we can express that most clearly, succinctly, generally speaking. So we're moving into Unit 3, or Module 3, which is about functions and function notation, and some properties of using those. And I'm not going to go through all the things that this has you do. If you've seen this PowerPoint on here, it's extremely long and goes over a lot of things that aren't what I wanted to focus on today. But the idea is if you have very small corners, you're going to get a box that looks more like a trough or a tray. If you have larger corners, it starts to look more, kind of equal, although it's always going to be rectangular in nature since the paper was to start with. And if you have extremely large cutouts, you're going to get something that looks like more like a cereal box sort of shape. just thinking of how this was generally. Let's see if I can get back to this. If I have an 8.5 by 11 sheet of paper, just one thing to think about this. Those square corners can only be so big. Obviously, I can't make them smaller than 0. And with my cutting ability, I couldn't really make them smaller than 1/2 of an inch. What's the largest, though, or what's the upper boundary for what size those corners could be? Smallest would be like, well, slightly larger than 0. How large could I make those? Obviously, I could make them 3.5 at least. Any thoughts?
Maybe 4.25.
4.25. So let's see, where'd you come up with 4.25?
So 8.5 is the length of the smaller side.
Okay.
And so if you divide that by half, then that would just completely cut off.
Yeah, so I don't want to be either. If I'm at 0 inches, then I don't have a box. I have nothing to fold up. If I'm all the way at, let's see, getting larger, so this smaller side, the 8.5 inch side is getting smaller and smaller here. I can see that if I were to slice it right up the middle, I wouldn't have a box either. And that sliced right up the middle would be at 4.25. So 0 to 4.25 is my range of values for the side lengths of these square corners. But at either extreme, it doesn't make a box anymore. So in terms of between, let's say I call that side length of the squares x. Just how much am I cutting off? Like how large are these squares? They're x by x. That x has to be between, but not including 0 and 4.25 in order to make a box. I could talk about what if it's 0, well, it's this, idea of a box that just isn't there yet, or 4.25, an idea of a box that, well, it completely disappeared because I cut off too much. So I guess you could kind of consider those to be in the range, but for actual boxes that have any non-zero volume, we need this side length to be 0 to 4.25, excluding those endpoints. So strictly between, not including, in terms of like, types of inequalities. So what if I have, ooh, and I apparently opened this up a few times. What if I have 0.5 as a side length there? And let me pull up a blank document of some sort. How about an Excel document? And zoom this in. All right, so if I have, let's see, 0.5 for x, this square length here, what's the computation that I do to find volume? Let's see, I actually want to put this under here. If I have x is 0.5, and let me just, there we go. To find the volume, what would I do? The length times width times height. Well, how long is, let's see, if x is 0.5, maybe kind of looking like this, and I go to find this, what's this longest length going to be if I have 0.5 as the square corner size? How many inches? 10 inches. Right, because it was 11. And then if I take a half-inch corner out of all these, by the time I fold up this longest side, there's a 1/2 inch missing on one side and a 1/2 inch missing on the other. So instead of being 11 long, it's 11 minus a half on both ends, so 10 long. Or in terms of this computation, I could say it's 11 minus 0.5 twice, so 2 times 0.5. I'm going to make this column wider. Oops, or try. There we go. And that's the long length. I'll just call it length. What about the width? Using the 8.5 inch side of the paper, if I cut off a 1/2 inch on each side, oh, yeah, it'd be 7.5. So 8.5 minus a 1/2 and a 1/2. So adding that on here, well, multiplying that on here. 8.5 minus 2 halves. And then what's the height of the box? 0.5. All right. Now, in terms of spreadsheet usage, this is not a very efficient usage of spreadsheets. I was typing this out so we can see what all is going on. But if I wanted to find that volume, really what I'm doing, I'm using this 0.5 a bunch of times. So I'm going to have, and I could still do this more succinctly, but if I want to have a nice formula, if you've played around with spreadsheets before, I'm going to have 11 minus 2 of that number in column B. So that's B2. Oops, and it's going to tell me to put a time sign in there because it's not a math program, it's a spreadsheet. 11 minus 2 x's, 8.5 minus 2 x's, B2s, and then times an x, a B2. Now let's see, I think it likes time signs all around. I don't know what version of spreadsheet I'm in here. But if I want this to compute that, I'll just put an equal sign in front and it says, okay, volume's 37.5. So if I had this side length of 1, I could do this whole thing again. It's kind of a mess. But just looking at this picture, if I have side length of these squares of 1, you think that's more volume or less volume than before? Kind of hard to tell because it's a little bit deeper, but it's also less wide. So the length and width gets smaller and the depth of this box gets larger. All right, so maybe it's about the same. If we want to do the computation with a 1-inch square corner as opposed to a 0.5-inch square corner, looking back at what's going to change, like, oh, well, these 0.5s are going to be 1s, yeah? So instead of writing it out, I'm going to write out just the numbers here. So I'd have 11 minus 2 times 1. And I'm not going to have this compute. I'm just going to leave it out here. I'm going to 8.5 minus 2 times 1. So 8.5 minus 2. Oops. And the depth of the box is now 1 inch, right? Or, so the way I set this up, this line pulls B2. If I just copy it down to the next line, it pulls B3. So it does come out larger. And this is 9 times 6.5 times 1. If I put an equal sign in front of this, you'll see it's the same, 58.5. Just leaving this out so we can see the computation that's done. All right, so 2, 3, 3.5. I could do the same sort of formula, subtracting that height of the box twice, or that square corner length twice. And have, for the case of 2, I'd have 11 minus 2 times 2, 11 minus 4. 8.5 minus 4. That's the amount that's left. And then it's 2 inches deep. So that would be the computation. Ooh. Sorry. Sticky fingers. Comes out to 63. So changing from 1 inch to 2 inches, the volume didn't increase very much. It increased just a little bit. It's twice as deep, but considerably less long. So it kind of balances out that multiplication of 3 numbers. Okay. So if I continue this with other measurements here, see, oh, 37.5, again, that's kind of weird. What are the numbers that are involved in this? If I had 3-inch cutouts, be 11 minus 3 on both sides, or we'd have a box that's cutting 3 inches off of each side. It's kind of this shape box. I forget what color that one was. But it's getting more cereal box shaped, but 3 inches off on each side is about the same volume as 1 inch off on each, or 1 inch square corners. Different shape, but similar volume. Actually, same volume for those particular ones. But this would be -3 on each side. 11 minus a couple of 3s. 11 minus 6 would leave us a 5. So it's not the same numbers here. We don't have the same numbers in the computation. We have a 5 and an 8.5 minus 6 and a 3, right? The height of the box is 3 in that case. So this one up here, just to write out what those numbers are, because it's kind of a mess. Now that we kind of understand this pattern, it was 11 minus 2 halves, so 11 minus 1, 8.5 minus 1, and then a 1/2 inch deep. So you can see it's this 37.5 and that 37.5 came from completely different computations, but their product is the same. All right, and again, with 3.5, that's going to be subtracting off a total of 7 inches from the length and the width of the original paper. So 11 minus 7, 8.5 minus 7, and then 3.5 inches deep. That's where that 21 comes from. These are the sizes of paper that we had. Now, just in general though, if I want to talk about, well, what about just for a general X? How would I express that volume, or what computation would I need to do? It would be like what I had here in the first place with all the -2 times somethings, right? I'd need to have 11 minus 2 times x, 8.5 minus 2 times x, and x, right? So in terms of a formula to compute, it's kind of messy, and here's a strategy. If you're trying to write a general formula and you don't really know what it looks like, try with some specific, and we talked about this, I think, on Tuesday. Try with some specific numbers. Like, what would I do if this was a 3? What would I do if this was a 1? Does this even work if this is a 1? Those are all kind of important questions to think about. Like, how does this work with regular numbers? Because that's all a formula or an equation or a function rule is. It's an expression of, in general, what's the computation that we need to do in order to get the result we want. So if you can do it for specific cases, maybe try a couple of them, and just in case you happen to pick a weird one, like you tried with 4.25 for some reason. You're like, oh, this is bizarre. This isn't working out well. Or if you tried 5. But in any case, we could call this a formula for our volume. And this that we were coming up with before, the fact that this x needs to be between 0 and 4.25. We'll talk more about that on Tuesday next week. But this expression for what sort of x's are allowed, what sort of starting points or input values given information is even sensible to use, that's called the domain of the function, like what you're allowed to put into it, what realm it exists on and makes any sense. In the cases of something like this, there's nothing about multiplication in general that says you can't use negative numbers or numbers like 17 or whatever you want. But in terms of this problem where x is representing an amount that we're cutting off of an 8.5 by 11 sheet of paper, practically speaking, so sometimes called a practical domain, we have some limitations on what values make any sense for the problem. So there's two sorts of domain sort of issues, but domain is just talking about, generally speaking, the legal or sensible values to sub into a formula and a function. Whether it's a function or not, there's still a domain. Any sorts of equations or formulas might have sensible or reasonable input values. But there's two senses of that. There's like the what will work out mathematically and give you an answer of some sort. And then there's the what actually makes sense in terms of what you're using this for, like what you're trying to compute. If it's a generic formula like f of x or v or q or t, and it's just some letters thrown together, you want to do things like avoid 0 as a denominator or square roots of negatives, because those generally are things to avoid. But I mean, this doesn't have any denominators or square roots or things like logarithms where you can only have certain types of numbers that go in. It's just in terms of this problem, this is what's called a practical domain. And in terms of applications, story problems, that's usually what we're talking about. A practical domain, just referred to as domain, is just generally speaking what makes sense in the problem. So I'll put this more as sensible input values. So domain is just talking about what you plug into a formula, and depending on what kind of formula it is, it's not necessarily one thing is called an input and one's called an output, but just thinking about what you're starting from, regardless of how that may be seen later. What are you allowed to substitute in? What makes sense in terms of a variable or an unknown that you see in terms of a value that you can put there? So this whole way of writing this here, this kind of a mess, but you can see, I just did this so I could do the computations. But if I wanted to explain some things, I say, well, when this square corner length that I cut out is 0.5, the volume is 37.5. And then it gets larger. When an x is 1, I have a volume of 58.5. When x is 2, volume is 63. When x is 3, and so on. Or when the volume is x, I have this expression that would compute the value in general. Instead of having to say whole sentences about that, we have function notation. Function notation is useful for describing the pairs of numbers that coordinate together, or even if you don't need to know what the value of the output is, just to express what something's about. So I want to talk about function notation, just briefly, which I hope you've seen before, but just to kind of refresh on what it is, what the pieces do, what they don't do, and then we're going to do some practice at writing things using function notation. So let's see, where do I have this? Maybe. There we go. All right, so moving on from boxes. So a distance d that a motorcycle travels from an intersection, measured in miles, is a function of the time elapsed in minutes since leaving the intersection. Blah, lots of words there, but we're defining some things that are going on. Motorcycles traveling past an intersection. There's some elapsed time that we're measuring, and the relationship between the time and the distance is called relationship G. Okay, G has nothing to do with abbreviations of motorcycle or intersection or distance or time, just random letter. But function notation, so not a multiplication just demonstrated here, but just function notation. If the name of this relationship is G, thinking about something about motorcycles and distance and time elapsed, any thoughts on what this could mean? What this expression G of 8.3 might mean relative to this situation? So if this is a function G, or relationship G, that relates distance that a motorcycle's traveled and an amount of time elapsed. Let's see, so distance, we might be able to find speed, but if this G is just relating the distance and the time, we can have it be one of two ways. It doesn't really say here, it's vague the way it's stated, but this could be a formula where the input, this is G is maybe some formula where the input is about time and the output is about distance, or it could be the other way around, it doesn't say, where the input is something about distance and the output something about time. But this function, this relationship called G, is something that relates the distance and the time. So those two are the input and output of some relationship, some function. In this case, I'm going to call it that. And this G is called the name of the function of this relationship. So I'm just going to pick one because it's kind of vaguely worded. It could be either way around. But let's say that G is a function whose input is something about the time just abbreviation, and the output is something about the distance. So relative to this, I'm just abbreviating briefly here. So if the input to this function is about time and the output is about distance, then this expression here, if you remember working with function notation before, when you say f of something or g of something, the something that's in those parentheses is what you're putting into the function. What's in the parentheses is the input value. So this is something then about 8.3 as a time, and to go back to the problem that has it all written out, this is elapsed time in minutes. So this is something about 8.3 minutes. So the 8.3 is representative of 8.3 minutes. G of 8.3, the whole thing there then, would represent the value that I get, or as the output, the distance after those 8.3 minutes. So this is telling us three things. If we have all this stuff defined up above, and like I said, make a choice. If you're writing it, you can do it however you want. So I just picked, let's say that the input is the time and the output's the distance. So I could write that as another sentence at the top, because it doesn't say. But, hi, frozen. There we go. When you see something like this, we want it to represent a lot of things. It's not a computation that you have to do necessarily. This just sitting on its own can be an expression for it. Kind of like on Tuesday when I said, well, just write out an expression for the computation you do for the height of the flag. Don't worry about actually doing it. Just write something that would compute it, because it's weird decimals. Same thing here. Maybe there's a whole weird complex formula. Don't do the computation. Just write out this to represent the value of what's called the dependent variable, or the output. In this case, the distance in miles. So G of 8.3 is some number of miles that the motorcycles traveled. But I can tell from this that I'm talking about this relationship between this relationship called G that relates the 8.3 minutes to that variable. So G of 8.3 tells us that, we're dealing with this relationship between distance and time. Time is 8.3. G of 8.3 means the distance after 8.3 minutes have elapsed. So this tells us kind of all of that together. It tells us we're talking about the relationship between distance and time because we've got that symbol G. It tells us we're talking about time 8.3 because we've got that 8.3. And by saying G of 8.3, that means we're talking about the distance that this motorcycle's traveled after 8.3 minutes from passing the intersection. So this symbol on its own, G of 8.3, doesn't mean you have to compute something. It can also just be a placeholder for a computation. It can tell somebody else looking at this, I want to reference how far the motorcycle's traveled after 8.3 minutes. I don't want to compute it right now. I don't want to worry about the formula for it. I just want to talk about it. So I'm going to write that down. So similarly, and I'll get back to that in a second, thinking about all this mess, if I want to be able to reference the volume of those boxes when the side cutout length is something you don't have up there, 2.5. Well, if I define a function, so all I have right now is volume and x. So I can say that V is the volume, and it would be in cubic inches because we had inches for our measurements on our paper. X was the length of the square cutout from each of the corners, the side length. From each corner of an 8.5 by 11 sheet of paper. And so let's say that I say F is the relationship between x and v. In fact, what I want to say is, let's say that x is our independent variable and v is the dependent variable. Or the abbreviation for that in math, so I'll write that out. X is the independent variable in this relationship, or the input, and v is the dependent variable, or the output for this function f. So these three parts put together, let me make this wider so I can, there we go. Those three parts, if I want to state that in a symbol, I can, well, in a brief math relationship, I can say v equals f of x, like that. And this tells me that instead of writing out all this, x is the independent, v is the dependent. If I'm making up a function and I want to tell you how it works, what goes in, what comes out, this is the way you can say that. Let me make this a little bit larger. Those statements always look kind of like a mess. Like lots of times you see y equals f of x. Like, yeah, y is the same as f of x. Well, y is the symbol that represents the output, and f of x tells you that I'm using a function f with input x. So having the whole thing there describes what I put in, what I get out, and what the name of the computation I'm doing, or what the name of the formula is that I'm using. So the name of the formula in this case is f, generic kind of letter that's often chose for functions. I could call it something else, G, Q, L, M, pick a favorite letter. It's kind of useful to not call it v of x, because I want to talk about like just v is the volume, x is the side length, and f is the thing that relates those two. So we have like three pieces. So f is related to that formula, or I could say f of x equals this 11 minus 2x times 8.5 minus 2x times x. And obviously you can write those three pieces, length times width times height, in whatever order you wanted to. It's just multiplication. But thinking about this whole table of things up here, if I want to refer to this number without needing to know it, I could just say, oh, well, that's f of 0.5. Right? F of 0.5 has this value, but by calling it f of 0.5, or saying, maybe even saying f of 0.5 equals 37.5, I'm saying when the side cut out is 0.5, I get a volume of 37.5. So this is v equals f of x. This is the v value over here. It's just in the other order. I could say 37.5 equals f of 0.5. Do that with the next one. 58.5 equals f of 1. V equals f of x. It's that same, this is the generic statement that tells me how the relationship works. Here's a specific example of it. And because we know the formula, we worked that out earlier. We know how volume of boxes works. We thought about it a little while. But I can refer to each of these numbers then. So I could just say, oh, 37.5, that's also f of 3. Now, f of 3 and f of 0.5 have the same value. That's okay. We're allowed to have the same result as many times as we want. You could have the same result for every single number if you have a constant function like f of x equals 19. Is that going to be the case for this box? No. But whatever it might be that would have a function that you bothered to write out like that, it's possible to have functions whose, for any input, have the exact same output. It's just not very interesting. So for this box situation, we have different inputs. They vary as the cutout varies in size, but we happen to hit the same value a couple of times, and that's okay. What is not okay in terms of function stuff is if I've defined this to be a function and I plug in a number and it's like, well, what's the answer? it kind of depends. Is it Tuesday or Thursday? It's like, wait, no. If I have a relationship between these, and you've written out the whole relationship in this function rule, when I plug in a number, I should definitely get one result. I should not get two results, or a maybe it's something else. For every input to a function, there's only supposed to be one output at most. It's not a, well, it depends on something else. Because if it depends on something else, that needs to be built into the formula. It needs to specifically define, at most, one output. Like I said, it's possible to pick it as something that you shouldn't have for an input and get nonsense for an answer, like a division by 0. That's why I say at most one output. You could get no output for something that's outside of the domain. But if you're picking numbers in the domain of the function, you should get one output for each input. They don't have to always be different. That's okay. You just have to, only get one at most. All right, so let's go back to what we were talking about here. So this g of 8.3, based on, like I said, let's suppose that the input is the time and the output is the distance. Or in other words, d equals g of t. I guess it didn't even say t up there, just function of time. D equals g of time, whatever symbol we're going to use for that. That's all of this. The dependent variable value, or the output value, is the whole thing, g of something. G is the name of the relationship that tells us what things we're relating, and the thing inside the parentheses is what you would plug into the formula, or the input that usually it's the part that you get to choose. All right, so let's say I have a non-story problem function. Let's say I just have something called f of x equals 3x squared plus 8x minus 17. So there's a rule for this function given, not just a description, oh, this relates time and distance. But maybe it does. Maybe this relates time and distance of something. If I see f of 2, in this case, I could compute that, right? Because I have a formula that tells me how to. But I don't have to. I could also just think of this as, well, it's the output from that formula. It's the result I get if I substitute in x equals 2. So f of 2 means the result I get from subbing in 2. Do I have to do that to be able to say that? No. I can just say it's what I'd get if I subbed in 2 for x. F is the relationship. 2 is what I put in. And f of 2, I don't have to compute it if I don't want to. I can just write f of 2 as a representation of that. Say, oh, 2 comma f of 2 is an input-output pair. Do I want to find f of 2 right now? Yeah, I could, but I don't really feel like it. I'm not feeling like doing arithmetic right now. I'll write f of 2 instead of writing out a number value for that. Plus, it reminds me what it is. It reminds me, oh yeah, I'm supposed to be finding the output from this function. So, function notation then. I will post a copy of just this worksheet as a link also. This, like, I didn't print out copies of this is a worksheet sort of thing. Let me zoom this in from me typing on it to you looking at it. There we go. So, I'm going to give you some time to look through these questions, but the definitions that we're going to be using we're going to do 2 different examples. Definitions we're using for this first example are up at the top. I'm going to have to scroll past that to see all the rest of this side, so you might want to jot this down. But let t be the time elapsed, this time in seconds, not in minutes like the motorcycle. So t is the time elapsed in seconds since a race car first started moving. Let's say that d is the distance in feet traveled by the car since it first started moving. So go, whatever. And then let's say that w is the name of the function to relate d and t, and it's defined. Let's say d equals w of t. So distance is a function of time, or time is the input, distance is the output. W is the name of the function that relates them in this case. So in boldface, you can see this reminder. Think of this as meaning when input t is used with function w, the result is a value of d, distance. All right, so T is time in seconds, D is distance in feet. And I've got, let's see, 4 questions to think about here. I want you to try to represent using function notation the things that are listed in A through D. So A, you don't have to compute anything. We don't have a formula. I don't know how fast this car is going. I don't know. We just have function notation to express things. So for part A, how would you represent the distance traveled by the car after the first 9 seconds have elapsed? Part B, the distance traveled between time 2 and time 5. Part C, the distance traveled in the 4-second time interval that begins 3 seconds after it started to move. So think about what time interval that is. And then part D, the distance traveled during a 7-second time interval that begins at a general time t equals x. So we're talking about distance traveled during an interval, a change in distance, delta D. D final minus D initial would maybe be something to think about here. All right, so I'm going to give you a little while to work on this. You can compare notes with neighbors. I'm going to wander around. You're going to think about function notation, but also linking it back to some of the stuff that we talked about last class period and last week. just make sure we're kind of on the right track notation-wise here. I wanted to answer question A, representing, not needing to compute, because I have no idea, I have no formula, just the name of a formula. Representing the distance traveled after the first 9 seconds have gone by. Using our function named W, what would I say? W of 9, yep. And that capitalized it because it wanted to. Okay. And so W of 9 is how far it traveled between the beginning and time 9, since it started, because that's what W is based on, since it started moving. The other 3 are asking for distances that happened over a closed interval, a change in the distance traveled between one time and another time. Alright, so for part B, this wants to know the distance traveled by the car between 2 points in time. I don't have a formula that, like, I just plug in a single number and I get between 2 points in time. The only relationship I have is how far it's traveled since it began moving. How can I use function W here to do anything with how far it traveled between time 2 and time 5? Any thoughts on what I could do with function W? Yeah.
I did W times, in parentheses, 5 minus 2, and then it would be like final minus initial.
Okay, so I like the 5 minus 2. If I do W of 5 minus 2, that's not quite what we want, because this would be W of 3 then, which is W of 3 would mean the distance it traveled by 3 seconds after it started. But I do want to do subtraction. How about this? So W of 5 on its own tells me where the car is, how far it's traveled after 5 seconds. Maybe it's traveled 100 feet, I don't know. Or what are we measuring in? Meters, feet? Feet? Okay. Maybe it's traveled 100 feet. Presumably, it would have traveled fewer feet by time 2 than it had by time 5. But these two things here subtracted, these are both, this is a distance that it traveled by time 5, a distance that it traveled by time 2, distance from the start. So if it was like 100 at time 2, if it was at 60 feet, and at time 5, it was at 100 feet, and I subtracted those, that would tell me the 40 feet that it traveled during that time interval. But what I'm doing here, the concept that we're doing is, I'm looking at D final minus D initial, right, or delta D. Let's see, I don't know where I have a delta on here, easy to get to. Oh, there it is. Delta. I just used it apparently. It's some sort of change in distance. And you get a change in distance, final minus initial, for whatever it is, x's, y's, d's, q's, whatever it is, by doing a subtraction of two different values of your variable that you're concerned with, the quantity that you want to know the change in.
Wouldn't you like divide it by
So if I'm just looking for distance, yeah, but that would give us something that we're going to be talking about a little bit later in the semester, or we talked about something related to that earlier, but not with function notation. If I divided this by 5 minus 2, if I took this expression, which is how far it traveled in a specific interval of 3 seconds, and then divided it by 3, what could that mean? A distance divided by a time. Rate of change, yeah. And so if I did that expression, W of 5 minus W of 2 over 5 minus 2, or over 3, that would give me a number of feet divided by a number of seconds, give me feet per second. Yeah. So that isn't what I was asking for here, but that's a computation that is commonly done with this sort of notation, because it's really kind of a pain to do all the computations in advance, so it's nice to kind of write it out that way. It's also something average speed. That would be an average speed over that 3-second interval. That's something that we talked about, average speed. Well, you talked about with Mr. Brownstein probably last week, and you did some problems with that over last weekend. But average speed, again, isn't taking a bunch of speeds and adding them up and dividing by how many there are. It's not that sort of average. Average speed, the way that it's normally defined is it's the constant speed that would be required to accomplish the same amount. So in this case, the constant speed that would be required to travel that far in 3 seconds, however far W of 5 minus W of 2 is. Maybe it's 40 feet, maybe whatever it is. But if I want to know the distance traveled during an interval, if I can figure out how far I've traveled at the beginning of that interval and the end of that interval, and I subtract them, then I know where I am in between. So it's kind of like, well, I need to know how far I drove between 7 o'clock and 7:15 this morning. Well, if I know where if I just have like my distance from home, like my phone started tracking how far I was from home, and neither of those were at home. Like maybe it's like, oh, well, you're 2 miles from home at 7 o'clock, and you're 8 miles from home at 7:15. So that meant I drove 6 miles between 2 and 8, between 7 and 7:15. So if I don't have information about where I am at every point in time, but I have how far I traveled relative to something, how far this car traveled since it started moving. So I can find how far it traveled during any interval by just subtracting its total distance traveled at the beginning and the end of that interval, final minus initial, to find the change in that distance traveled, or the distance traveled during a specific interval of elapsed time. All right, so take another couple minutes, see if you can, if you worked on C and D before, maybe clean them up a little bit. I'll leave this there, and there's a question 3, there's parts of it at least at the bottom there. If you already got parts C and D, figured out expressions for those. If not, think about C and D a little bit more. They're going to be similar to what we did for B, just different pieces, known or unknown, or described differently. But then at the bottom, there's some expressions with W, function W. I'm going to talk about what those mean too, but take a couple minutes and see if you can think a little more about C and D, see if your answers make sense based on what we just talked about. I know this is maybe a little weird. We don't have a formula to use. So I appreciate your input on this. It's not easy to get into just writing symbols as opposed to doing computations. is your index. It's actually have all the time information you need. It's just a matter of translating that into usable format. Alright, so, again, question B is maybe phrased the most directly, even though it's confusing still, but if we talk about the distance traveled between time 2 and time 5, and we want to find that, we did W of 5 minus W of 2, final distance minus initial distance, for that interval, beginning and end of the interval, distances traveled subtracted, give us the distance traveled during the interval t equals 2 through t equals 5. So in question C, we want the distance traveled by the car in a 4-second time interval that begins 3 seconds after it started to move. What values of t is that? T equals what through what? Yeah.
I got 7 through
Yeah, 7 through,
7 to 4.
or yeah, 3 through 7. So yeah, 7 is going to be the final and 3 the initial. So yeah, we've got t equals 3 through t equals 7. And AutoCap, stop doing that. So if this is a 4-second time interval, 3 through 7, starts at 3 seconds after and goes for 4 seconds, that's 3 through 7, and we want the distance traveled during that interval. Now it's phrased the same way as the previous question. So to do that, we can do d final minus d initial. So W of 7 minus W of 3 and W of 7 minus W of 3 represents the distance that had traveled by time 7 minus the total distance that had traveled by time 3. So by subtracting those two, we find the distance it traveled in between those 2 points in time. All right, now, what about part D? What time interval is this? It says the distance traveled during a 7-second time interval that begins at a general time t equals x. So that's t equals x through what? X plus 7, good. So x plus 7, or 7 plus x, either one of those is fine. They both add in the same order, whatever. So if I think about doing, again, the same thing, and this is a lot of what, math gets more complicated. It's ideas that we started with, and they were simple and there were lots of numbers. And then we're trying to generalize that or express more generic situations, or if you can relate a more complex sounding situation to something that you did earlier, you can probably use the same techniques and same concepts to solve the problem. It's just a matter of, can I use more symbols and fewer numbers and still write what I mean? If you have function notation, we can do this. I can say, oh, okay, then we're going to have what expression with w's to represent the distance traveled between t equals x and t equals x plus 7. You're going to have w of, x plus 7, final, minus initial, right? W of x. And I don't know what x is. I don't know what this formula w is. But I can write an expression that represents that. Now, these subtraction expressions then, with w of something minus w of something else, when you see those, if you're trying to interpret what does this mean, think, oh, maybe this is a final minus initial, or a larger minus a smaller. It's going to find a difference or a delta, a change between two different input values. And it doesn't have to be time, it could be a different concept entirely. But thinking about these expressions below, you'll see 3 of them have subtraction, just like what we had. This middle one's a little different. But thinking about if you just saw this expression written, whether it's you're working with someone else on homework and they had something written, what could these potentially mean relative to the car? Now, obviously, it could be lots of weird things when there's random numbers thrown in, but w of 5, for instance, what should w of 5 mean using our definitions from this problem? Yeah, the distance traveled after 5 seconds. So the total distance from when it started moving to 5 seconds is w of 5. So just as a note here, maybe you're thinking about this, like, wait, if it's distance traveled between the beginning and now, shouldn't it be subtraction? I could say something about this. W of 5, if this is the distance traveled between when it started moving and time 5, I could also say it's w of 5 final minus w of 0 initial. But because of how this function w and distance and time are defined, it's distance traveled since it started moving. So at time 0, even though we don't know anything about function w or how fast the car is going, because of the way it's defined, w of 0 would have to be 0, right? The distance traveled since it started moving, if it has traveled for 0 seconds, is 0. And many times you'll see things like that. That's kind of, it's a fact that you know because of how the variables are defined, how the function is described. Not always. But in this case, that's the same, which is why even though this is distance traveled, it doesn't have a subtraction in it because it's kind of implied. W of 5 on its own means the distance traveled from the beginning to time 5. What about something like 2 times W of A? Well, the W of A is kind of generic, but we could say what it means based on the definitions of our function and what the input means and what the output means. Any thoughts for 2W of A? Yeah?
One idea would be that it's the combined distance of 2 cars that are starting in the same place but traveling in different directions at the same speed.
Okay, yeah, so this could be 2 cars traveling for A seconds at the same, whatever the same rate is, and it's the total distance that they've both traveled, like added together, or if they've moved apart from one another, it would also be how far apart from, if they're going opposite ways, how far apart they are from one another at the end. It could also just be 1 car, and we're just saying something about twice as far as that car's gone. But yeah, there's definitely something about a twice or 2 times as much, and so we could make a story about 2 cars. We could just be doing some computation with twice as far, but that's just a times 2. So just to point out, if W of A is some sort of distance traveled, then multiplying by 2, we'd still have a distance by the time we're done. It doesn't change into a speed or anything like that. Times 2 with no units on it is probably just 2 times as much distance. Just kind of like when we're working with these subtraction problems, if one is a distance and the other is a distance, what we get as a result should be a distance. It's just a matter of describing. So based on what we did in the earlier problems, W of 10 minus W of 8, what might that indicate? Somebody else? Anyone want to take a guess at what I could say that would maybe mean W of 10 minus W of 8, or what's the meaning of? Yeah.
How far the car traveled between 8 and 10 seconds.
Yeah, how far the car traveled between time 8 and time 10 seconds into this, whatever it is, race. It's a race car. All right, so this would be a distance traveled between those 2 times. Now, what about part D? It's subtraction, but notice it's not W of 9 at the end, it's just 9. Any thoughts on this one? Yeah.
Wouldn't it be that change in W's recorded after 9 seconds or recorded after some static variable?
Yeah, so what, in order for this subtraction to kind of make sense, what sort of thing should 9 be? What kind of units in order to subtract it from W of 7.5? Probably, yeah, it should be like another distance of some sort, right? If W of 7.5 is some number of feet traveled, and I'm subtracting 9 from it, in terms of, if this were a sensible expression, it probably wouldn't be feet minus seconds or something like that. Like 9 could literally be anything in reality. But if this expression is going to have a meaning, and I'm subtracting things, they need to be the same types of things. So like feet minus feet. So I don't know what number of seconds goes with this time, with this 9. That should maybe be a number of feet traveled. But I can say it's 9 feet. So, yeah, thought?
Yeah, question. So if you set an equal sign to the end of that after the 9, and you just have like just a variable at the end, couldn't you swing the 9 over and have it be like the y-intercept or like the initial condition?
Yeah, if I knew what this equaled. So let's say that this is, I don't know, like I did the subtraction and I got 230. Then I would know that W of 7.5 is 239, right? Which, what if this W of 7.5, this is how far the car traveled in 7.5 seconds, some number of feet, and then I subtract 9. Whether I know what it equals or not, that number would be like 9 feet less than however far the car traveled in those 7.5 seconds. Because in order for it to make sense, I'm hoping that that 9 is something about feet. Otherwise, it's just weird to subtract. It's like if I had, oh, well, I had 5 classes, but then I took off 2 hours. So 5 minus 2 is 3. I have, wait, no, that doesn't make any sense. There's no reason to subtract things that aren't the same sorts of units. You could leave them next to one another, but the meaning of it is kind of a mystery. So whether we have a number result for that or not, I could move this over, and then that would tell us another fact. And in fact, if this had been 230, like I said, we could move this over and say W of 7.5 equals 239 then. And if we knew that, then hey, we know exactly where we were at time 7.5. So great, we would travel 239 feet. All right, last bit, and I'm going to post this set of questions, plus there's some more that we didn't get to that are about height of a water in a sink. I'm going to ask you to look at those before class next Tuesday. I'm going to post them just as a link on Canvas to get to. But this last question here, let's just finish up this last one that I had about race cars and traveling. here's another subtraction. So W of 3 plus H minus W of 3. That would be a how far it traveled between sort of question, between when and when. Yeah.
I would say it's any interval after 3 seconds.
Yeah, this would be the distance traveled, distance traveled after 3 seconds, and I don't know how far after 3 seconds, up through H seconds later. So between time 3 and mystery time, sometime or H seconds later. That H would have to be something about seconds for this to make sense, just kind of like the 9 would have to be something about feet for that previous one to make sense. So between 3 and 3 plus H as values of time, and I don't know what H is, but it's 3 plus H would be H seconds after 3, however big H is. And H could actually even be negative. So between 3 and 3 plus negative 1. It's like, okay, between time 3 and 2. That would be a weird way to do this. It'd give you a negative result if the thing were going forward. But again, just interpreting the expressions, things to think about. What are the units on the numbers that you see? What are the values of the whole expressions, or what sorts of units do those whole expressions have? W of something is going to be a number of feet in this case. But the something, the part inside the parentheses, is a number of seconds, or an expression for a number of seconds. All right, so I realize there are no other visible assignments right now. I'm going to have up some assignments from sections 3.1 and 3.3, actually, in the next half hour or so. They're not going to be due until after the weekend, but they're going to be related to what we've talked about yesterday and today, relative to, or not yesterday, Tuesday and today, relative to some extra things with absolute value and distance formula, but mostly function notation and writing expressions with function notation. All right, so I will see you on Tuesday, but I'll have some questions including this and the next half hour.